Welcome back to Unit 6 on equations. Now that the concept of the preservation of equality has been established, we are going to return to the idea of solving linear equations. In Section 3, we will use modeling to do this, and in Lesson 1, we do so using our two-pan balance. So recall, what does it mean to solve an equation? We are finding the specific value or values for the variable that make the equation true. In grade 7, these equations will only have one solution. Only one value will exist to satisfy the equation. As you encounter different types of functions in the future, there may be some equations whereby you will have 2 or 3 or maybe even 4 solutions. But for now, we stick to one. We have already examined systematic trial and inspection. Now we use a modeling process involving balance scales, our good old two-pan balance. We will isolate the variable to determine its value. In other words, get the variable all by itself. Our first example, f plus 4 equals 9. Our job here, we have to solve for f. We have to get f all by itself, isolate it. To do that, we're first of all going to represent this equation on our balance scales. So we're going to use our hexagon for our variable, and we have one hexagon, because as you recall, there's a 1 understood to be in front of the f in our equation. We have a mass of 4, and on the right-hand side, a mass of 9. So this corresponds to the left-hand side of our equation. This corresponds to the right-hand side of our equation. To get the variable f by itself, we need to remove the mass of 4. Here's where the preservation of equality comes in. Whatever we do to one side, we have to do to the other. Now on the right-hand side, we have a mass of 9. So in order for me to be able to remove a mass of 4 from both sides, then we have to take that mass of 9 and break it down into a mass of 4 and whatever's left over, which would be a mass of 5, because 4 plus 5 gives us 9. So in this second step here, I've replaced the 9 with a 4 and a 5. Now we can remove a mass of 4 from both sides. Let's do it. There they go. What are we left with? Well, we've isolated the variable. We have that hexagon all by itself on the left-hand side. And what does it correspond to? Well, on the right-hand side, we have a mass of 5. Therefore, f equals 5. We have solved the equation. And we're going to verify this. So to verify, in my little block here, I'm going to put f plus 4, and I'm going to put a circle because I'm going to see if it equals 9. So the value for f that we have found is 5. In place of my f, I put a 5 plus 4. Is that going to equal 9? Well, one more step will tell us that. 5 plus 4 is indeed 9. And yes, 9 obviously equals 9. Our solution checks out. Therefore, f equals 5. Second example, 3p equals 6. On the left-hand side of our equation, we have 3 hexagons. And on the right-hand side, we're going to have a mass of 6. So I put a p inside of each hexagon to represent the 3p. And a mass of 6 is on the right-hand side. Our goal here is to get one hexagon, 1p by itself. So to get the variable p by itself, we have to break down the mass of 6 into 3 equal groups, which will then correspond to the 3 p's on the left-hand side. If I want to take 6 and break it down into 3 equal groups, that's going to give me 3 masses of 2. We can group each p with a mass of 2. And then what that tells us, of course, is that p equals 2. We have isolated one hexagon, one P, and that P corresponds to a 2. We have solved the equation. Let's verify. I start with my 3P. In place of the equals, I'm going to put a circle, and I'm going to check to make sure that the value that I found for P actually works. So 3 times 2, which is what we found P to be, does that equal 6? Well, 3 times 2 is 6, and most definitely 6 equals 6. Solution is found. One more example. 5 plus 2x equals 11. To represent this, on the left-hand side, I have a mass of 5. I have 2 hexagons to correspond to the 2x. And on the right-hand side, I have my mass of 11. What do we need to isolate? What do we need to get all by itself? We got to get one of these hexagons all by itself. So what are we going to do here? Well, our first step in getting the variable x by itself, we're going to remove the mass of 5. But remember, if I remove a mass of 5 from the left-hand side, I have to do that on the right-hand side. Right now on the right-hand side, I have an 11, so I'm going to replace that mass of 11 with a 5, and then the remaining piece, which would be a 6, to make up the 11. Now I can remove a mass of 5 from both sides. Let's do it. So now what I'm left with are 2 hexagons and a mass of 6. Well, I'm getting closer. But remember, you need to get one hexagon by itself. So what we're going to do next is take that mass of 6 and break it down into 2 equal groups. And to take 6 and break it down into 2 equal groups, that will be 2 masses of 3. Now we compare them up. So that's going to tell us that each x is going to match up with a mass of 3. What have we just discovered? X equals 3. Let's now verify or check our answer. So we're going to see if x equals 3, does that actually work? So in the box here, I'm going to put 5 plus 2x, a circle in place of the equal sign, and then 11. We just determined that x is 3. So in place of my x, I put 3. And we're going to see if that does indeed equal 11. Order of operations, 5 plus 2 times 3 is 6. Does that equal 11? 5 plus 6 does indeed equal 11. In the circle now, I can put an equality sign, and we've just shown that x equals 3. It is indeed our solution to the equation. And now I'd like you to proceed to the activities for Lesson 1.